All right, guys. So chapter 7, power series method. So in this chapter, we want to see the connection between power series functions and how to use them to solve differential equations. So power series is a concept you learn in integral calculus in the topic of series. So we have to review that topic first and remind about some basic definitions and concepts related to power series, and remind ourselves about some basic properties so that we can use those properties to solve differential equations. Now, well, first in Math 113, you learned about linear approximations, and you learned how to approximate a function using a linear function. So you saw that if f of x is a differentiable function, then we can approximate f of x as f of a plus f prime of a times x minus a. Now this equation here is the equation of tangent line to f of x at x equals a. So if you look at this picture, you can see that if this is, let's say, graph of f, a differentiable function, and let's say if you have a fixed point a, then f of x, the values of f of x will be close to the values of this straight line as long as x is close to a. So the best approximation, the best linear approximation for the function f of x for a close to a given fixed point x equals a is basically the tangent line at x equals a. The tangent line at x equals a will be close to the graph of f of x as long as x is close to a. Now, if you choose x closer to a, you will have a better approximation for f of x. So basically, this is the first level. We can approximate the function using a linear function. But if you want to improve the approximation, we can include more terms, and we can go into like the quadratic term or cubic term and continue this until the nth degree polynomial. So basically we can say that we can approximate f of x with this polynomial. When you look at this expression, it's a polynomial in x. And what is the degree of this polynomial? The degree of this polynomial is n. The highest power of x is n. And a is a fixed number here. Degree n polynomial, which is called the Taylor polynomial at x equals a. So we could write it this way: f of x approximated by f of a plus f prime of a times x minus a. So this part here is the formula we saw above for the linear approximation. And then this is the quadratic term that we can add to improve the approximation. And then this is the cubic term, and so on until we get the nth degree polynomial. So this whole expression is called Taylor polynomial at x equals a. Taylor polynomial of degree n at x equals a. Now, even if you use the nth degree, let's say even if n is a large number, let's say if n is equal to 100, still the right-hand side is a polynomial, and still we have approximation here. Here, as you can see, we have an approximation sign, and it's not equality. But how can we convert this into equality? If we want to have an equality here, we can make the right-hand side a series. If we make it a series, then the approximation can become equality. So then if we generalize this Taylor polynomial and include terms all the way to infinity, then we get a concept called Taylor series. So Taylor series is the same expression as here, but we don't finish at degree n. Instead, we continue forever, and we will get a series, which is an infinite sum. Series means infinite sum. So this is the Taylor series at x equals a. And now when can we say that f of x is equal to Taylor series at x equals a? So as we said earlier, once we replace this Taylor polynomial with Taylor series, now then we have a potential to have an equality sign here. Now, can we say that this equality happens all the time for any function f? In other words, can we say that any function f is exactly equal to its Taylor series? To answer this question, we need a definition, basically. The definition says the function f of x is called analytic if for every x equals a, the function f of x is exactly equal to t of x, the Taylor series at x equals a, on some open interval containing a. So if the function and the Taylor series are exactly equal to each other, then the function is called analytic. Analytic function means a function such that the function and the Taylor series are exactly equal, and the equality must happen on some open interval containing a, which means, you know, a little bit to the left and a little bit to the right of a. So in mathematics, when we want to talk about an interval that contains both sides of a little bit to the left and a little bit to the right of a, we would say an open interval containing a. So if f of x and the Taylor series are exactly equal, a little bit to the left and a little bit to the right of a, then we say that f of x is analytic. Now the question is, which functions are analytic? So most functions that you're familiar with and you have studied before are considered to be analytic, such as all polynomials, basic trigonometric functions, exponential functions, and most functions you have seen in calculus are analytic on their domain. So we can say that theorem all polynomials rational functions and y equals sine x, y equals cos x, y equals tan x, y equals cot x, and y equals e to the x, y equals ln x. All these functions are analytic on their domain. So on their domain, they're analytic, meaning that the function will be equal to the Taylor series, at least close as long as x is close to a, for every a in the domain of these functions. So for example, let's consider y to be e to the x. And let's set a to be 0. Then we know that this function is analytic on its domain. A domain of e to the x is all real numbers. So analytic on all real numbers, and in particular at a equals 0 will be analytic, meaning that the function will be equal to its Taylor series for x close to a, for x close to 0. So for x close to 0, e to the x is equal to its Taylor series What is Taylor series of e to the x? So we know that this can be written as f of 0 plus f prime of 0 times x plus f double prime of 0 over 2 factorial x squared plus other terms. Now, what is f of 0 here? So here, f of x is e to the x. So we can say that f of 0 is e to the 0, which is 1. And f prime of 0 will be also 1 because derivative of e to the x is e to the x itself. So the second derivative, again, e to the x, and all derivatives are e to the x itself. So then f of 0, f prime of 0, f double prime of 0, all these functions will be, all these numbers will be 1. Because all derivatives are e to the x. So if you evaluate them at 0, you'll get e to power 0, which is 1. So then the Taylor series at a equals 0 will be 1 plus x squared over 2 factorial, x cubed over 3 factorial, and so on. So this will be the Taylor series at a equals 0. Now the function is equal to e to the x will be equal to this function, the Taylor series, for x close to 0. So we can say that e to the x is exactly equal to 1 plus x squared over 2 factorial plus x cubed over 3 factorial for x close to a equals 0. Now, the question is, how close should I choose x to a equals 0 so that this equality happens? We know that if x is close enough, these two will be equal, but how close? Like, let's say from -1 to 1, for example, or let's say -1/2 to 1/2. How close should I choose x to 0 so that this equality occurs? The question is, how close should we choose x to 0, to a equals 0? So the answer is we have to choose x within the radius of convergence. Now, what is radius of convergence? So let me remind you about the definition of radius of convergence. So consider a power series of the form, let's say sigma an x minus a to power n from 0 to infinity, which is same as a0 plus a1 times x minus a2 times x minus a squared, and so on. So if we consider a power series of this form, now Taylor series is a special case of power series. So for power series, these coefficients could be arbitrary numbers. Now for Taylor series, we said that this one, for example, will be chosen as f of a, this one f prime of a, this one f double prime of a over 2 factorial, and so on. But the radius of convergence can be defined in general for a power series, not in particular for Taylor series. It can be generalized to any power series. So if I consider power series of this form, then we can define the radius of convergence. How can I define the radius of convergence? Then we can say there exists a number r, capital R, between 0 to infinity, such that the series is convergent for absolute value x minus a less than r, and it is divergent for absolute value x minus a bigger than r. So if you consider, for example, this is a, this will be a minus r, this will be a plus r. So here we will have convergence. When you say absolute value x minus a less than r, means you are between a minus r to a plus r. Here you have convergence. And outside of this interval, like here, you have divergence. And here you have also divergence. So convergent inside this interval, divergent outside the interval. And on the border points, which is a minus r and a plus r, then depends on the example. It could have convergent or could have divergent. So basically a theorem guarantees that there exists a number capital R between 0 and infinity, that convergence happens inside the interval a minus r to a plus r, divergence happens outside. And this number capital R, whose existence is guaranteed by a theorem that we are not going to prove here, but there is a theorem that guarantees this existence of this number capital R. So this number capital R with this property is called radius of convergence for our series. So this number R, such a number R, is called the radius of convergence for the series above. And note that on the border points, which means for x equals a minus r and x equals a plus r, meaning that for absolute value x minus a equals r, we may have convergence or divergence. And that depends on the example, depends on the function. So, and now the question is, how do we determine the radius of convergence? To determine the radius of convergence, you can use the tests that you learned in Math 114, such as ratio test or root test. You can use those tests to determine the radius of convergence. So remark, use the convergence divergence tests such as ratio test, root test, etc. To determine radius of convergence. To determine the radius of convergence. Now let's look at the example above. In example above, we saw that e to the x is equal to 1 plus x squared over 2 factorial plus x cubed over 3 factorial for x close to a equals 0. Now let's determine the radius of convergence using ratio test. Now, what was ratio test telling us? If you remember, recall, ratio test tells that if you have, let's say, sigma an, and from 0 to infinity, a series with positive terms, then if, let's say, we set rho as limit an plus 1 over an as n goes to infinity, let me say, then set rho as this, then if rho is less than 1, then the series will be convergent. And if rho bigger than 1, the series will be divergent. So here my terms are, look at the terms, 1 plus x squared over 2 factorial and so on. So here, what is my an? Here we have sigma x to power n over n factorial, and from 0 to infinity. If I want to write the series on the right hand side using sigma notation, I can write it as sigma x to power n over n factorial, and from 0 to infinity. So the first term will be x to power 0 over 0 factorial, which will be 1. Next term will be x to power 1 over 1 factorial, which will be x, and so on. Now, if I set, so here basically my an is x to power n over n factorial. So, but I want an to be positive. So let me take absolute value. So let's say rho equals limit absolute value an plus 1 over an, because x here, remember, x is close to 0. So it could be on the left side of 0 or right side of 0, meaning that it could be negative or positive. But if I take absolute value, everything becomes positive, and then I'll be able to apply the ratio test. So rho equals limit n goes to infinity of this, which will be limit absolute value x to power n plus 1 over n plus 1 factorial divided by x to power n over n factorial as n goes to infinity. And then this is same as limit absolute value. If I simplify, x to power n plus 1 over x to power n will be x. And n plus 1 factorial can be written as n plus 1 times n factorial. And then divided by n factorial terms will cancel out each other. And I'll be left with x over n plus 1 as n goes to infinity. And x here is a fixed number. The limit is over n. So any fixed number divided by infinity will be 0. So the answer will be 0, which is less than 1. So rho will be 0, which is less than 1. Therefore, we will have convergence according to the ratio test. So by ratio test, sigma absolute value, remember I've taken absolute value. So absolute value x to power n over n factorial, n from 0 to infinity, is convergent. Because remember, I saw that if I took absolute values, and why did I take absolute value? In order to make things positive so that I can apply ratio test. If I take absolute value, then the series becomes convergent. But what about by original series? There is no absolute value. I wanted to know under which circumstances the original series will be convergent. here I have to use another fact from Math 114 that if a series is absolutely convergent, meaning that if you take absolute value from the terms and still it will be convergent, then the original series will be convergent as well. So let me write it down this way. So far we said this series is convergent for every x, because remember the limit was 0 for every x. So for every x, this was convergent. Now again, recall from Math 114 that if a series sigma an and from 0 to infinity is absolutely convergent, what do we mean by absolutely convergent? Meaning that sigma absolute value an and from 0 to infinity is convergent. Then we can say that the original series is convergent. Then sigma an and from 0 to infinity is convergent. So here we said that we verified that sigma absolute value x to power n over n factorial n from 0 to infinity is convergent for every x between minus infinity to infinity. So that means the original series is also convergent. It's convergent for every x between minus infinity to infinity. So we verified that this series is convergent for every x. The series in the right-hand side is convergent for every x. So in this case, well, we were expecting x to be at least close, this to be valid at least for x close to a, such as -1 to 1 or -1/2 to 1/2. But we have a good news here that not only for that, those x values, the series in the right-hand side is convergent and convergent to the e to the x. It's actually, the series on the right-hand side is actually convergent to e to the x for every x between minus infinity to infinity. So here the radius of convergence will be infinity. Remember that radius of convergence, capital R, was a number between 0 and infinity. See, I allowed equality for infinity as well. So R is allowed to be 0, is also allowed to be infinity. In this case, we have convergence for every x between minus infinity to infinity. So that means our radius of convergence is infinity. So here we have radius of convergence for sigma x to power n over n factorial to be infinity. The series is convergent according to the ratio test. The series is convergent for every x between minus infinity to infinity. That means radius of convergence is infinity. So one theorem that I can mention here is that if f of x is one of the functions mentioned above, and if a is inside the domain of f, then f of x will be equal to the Taylor series T of x Taylor series at or around x equals a, for which x values? Well, so far we said for x close to a, but now that we learned about the concept of a radius of convergence, we can say for every x with absolute value x minus a less than r. Absolute value x minus a less than r. And here r is the radius of convergence of T of x. So look at the Taylor series around x equals a. Each power series has a radius of convergence. So in particular, a Taylor series has a radius of convergence. Call that radius of convergence r. Then Taylor series and f of x are exactly equal to each other for every x with absolute value x minus a less than r. If f of x is one of the functions mentioned above, one of the functions mentioned above means what? Means polynomials. Here we mentioned some functions, right? In the theorem here, polynomials, rational functions, sin x, cos x, tan x, cot x, e to the x, ln x. These functions. Or we can also consider composition of these functions. Composition of these functions can be also considered to be analytic on their domain. We can also mention here these functions and their compositions. So if you consider any of these functions or their compositions, we know they're analytic, meaning that f of x and the Taylor series are exactly equal to each other for x close to a. But now this new theorem says they are exactly equal to each other for which x value is close to a. How should it be close to a? How much should it be close to a? By radius of convergence. If you calculate the radius of convergence of the Taylor series and x is close to a by radius of convergence, then the equality happens. So let me call this one theorem star, just to specify which f of x I mean here. I can say for f of x, one of the functions mentioned above in theorem star. And if a is in domain of f, f of x and t of x are exactly equal for every x inside interval of convergence, a minus r to a plus r. So in example above, let me apply it for the example above. We saw that t of x equals 1 plus x squared over 2 factorial is the Taylor series for e to the x around a equals 0. And we saw it has a radius of convergence of infinity. So the theorem, because e to the x is one of the functions listed in the theorem star, so we can say e to the x and t of x are exactly equal to each other for every x with absolute value x minus a less than r, and a here is 0, r is infinity, means for every x with absolute value x less than infinity, which means for every x. So by theorem above, we can say e to the x, which is f of x, equals t of x, which is 1 plus x squared over 2 factorial, plus dot 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 for every x with absolute value x less than r, which is infinity, meaning that for every x between minus infinity to infinity. So we applied or combined these theorems to conclude that e to the x and Taylor series of e to the x at x equals 0, which is 1 plus x squared over 2 factorial plus dot dot dot, are exactly equal to each other, not only for x close to 0, but for every real number x. For every real number x, e to the x and this Taylor series are exactly equal to each other. Now, similarly, let me give an exercise. Repeat the process above. For y equals sine x, and y equals cos x, y equals sine x, y equals cos x, to conclude that sine x is equal to x minus x cubed over 3 factorial plus x to the power 5 over 5 factorial. Again, for every x between minus infinity to infinity. Cos x will be equal to 1 minus x squared over 2 factorial plus x to the power 4 over 4 factorial. Again, for every x between minus infinity to infinity. And also 1 over, if we give another exercise, show that 1 over 1 minus x is equal to 1 plus x squared x cubed, which can be written as sigma x to the power n from 0 to infinity. For which x values this time? For x between minus 1 to 1. Meaning that for absolute value x less than 1. For absolute value x less than 1, 1 over 1 minus x, and this Taylor series are exactly equal to each other. So this one is the Taylor series. So this is Taylor series. All of these are Taylor series at a equals 0. This one also Taylor series at a equals 0. And this one also Taylor series at a equals 0. So we know that these functions are analytic, meaning that Taylor series at a and the function f of x are exactly equal to each other as long as x is close to a. So here f of x, which is 1 over 1 minus x, and this Taylor series at a equals 0 must be equal to each other for x close to 0. But again, how close? Well, in this case, it turns out to be only by radius of 1. If x is between minus 1 to 1, then these two are exactly equal. But if x gets farther, then they are not equal. So the situation is not as ideal as the previous ones. Previous one, we said x close to 0, these two must be equal. But it turns out ultimately that not only for x close to 0, but for any x between minus infinity and infinity, these two, this function and the Taylor series are equal. But the situation is not as ideal in this case. In this case, the function 1 over 1 minus x and the Taylor series are exactly equal as long as x is close to 0 by radius 1, meaning that if x is between minus 1 to 1. So this is a equals 0. And if x is here between -1 to 1, then we will have convergence of t of x to f of x. And, or in other words, t of x and f of x will be equal. All right, guys, so these are some basic properties or formulas for Taylor series of basic functions, such as sine x, cos x, e to the x, and 1 over 1 minus x. So these are important formulas that you learn in Math 114 for Taylor series of these standard functions. All right, guys, now so far we have talked about analytic functions, the functions that are analytic, and with some most standard functions that we are familiar, such as polynomials, trigonometric exponentials, their compositions are analytic. But the question is there a function that is not analytic? So question here, which functions are not analytic? So first of all, analytic means what? So again, recall analytic, f of x is analytic. Let's say at x equals a, if f of x and t of x, which means f of a plus f prime of a times x minus a plus f double prime of a over 2 factorial times x minus a squared. These two functions are exactly equal for x close to a. Or like technically an open interval containing a, which is a term used in, like, for example, analysis course. But in this course, let me just to simplify the concept, I would just say x close to a. Now, look at the right-hand side. In order to calculate the right-hand side, I need all derivatives of f. Because in order to construct the function the right-hand side, I need f of a, also f prime of a, also f double prime of a, f third derivative at a, and so on. So the function must be differentiable of every order, of all orders at a, in order to be able to construct the function on the right-hand side. So if the function is not differentiable, or even not twice differentiable, or not third differentiable, or not differentiable of any order, then I will not be able to construct the right-hand side, and the function will not be analytic automatically. So if f of x is not differentiable of any order, meaning that like f prime of a does not exist, or f double prime of a does not exist, or third derivative at a does not exist, then f of x will not be analytic, since f of a plus f prime of a, the series will not be well defined. So for example, y equals absolute value x is not analytic at a equals 0, since f prime of 0 does not exist. So you sign math 113, that if f of x is absolute value x, then f prime of 0 does not exist, or the function is not differentiable at a equals 0. So if it's not differentiable at 0, that means it's not analytic at 0, according to what we just said. Or another example, let's say y equals, let's say x plus 1 if x bigger than or equal to 0, and x if x less than 0. Again, this is not analytic at a equals 0, since this function is discontinuous at a equals 0, so it is not differentiable at x equals 0, at a equals 0. If it's discontinuous at a point, it will be automatically non-differentiable. We saw this in math 113 as well. So it's not continuous, therefore not differentiable, therefore not analytic. So this is one situation for functions that are not analytic. If a function is not differentiable of any order, it will not be analytic. But now the more interesting question is, what about if it's differentiable of every order, so that the right-hand side can be constructed? Then can we say that the equality happens with f of x for x close to a? So next case, if f of x is differentiable of every order, meaning that every order at x equals a, meaning that f prime of a, f double prime of a, f third derivative at a, all these are defined, all these exist or are defined. Exist, they all exist. Then it is still possible that equality 2 star above does not hold. So let me call this one equality 2 star, that the equality that I want to know whether it occurs or no. If this equality 2 star occurs, then I will call the function analytic at a. If it doesn't hold, then it won't be analytic. So one way for this equality to not to happen is that, of course, to have one of the derivatives not exist, and in that case, right-hand side will not be constructed, will not be well defined, and it will not be equal to f of x naturally or automatically. But even if all the derivatives exist at x equals a, well, then we will be able to construct the right-hand side because all derivatives exist, but it is still possible that right-hand side is not equal to f of x. And then the function will not be analytic. So in other words, it is possible that a function is differentiable of every order, but it is not analytic. So a standard example here is f of x equals e to the minus 1 over x if x bigger than 0, and 0 if x less than 0. So here you can check that derivative of f at 0 exists and is 0. Similarly, second derivative at 0 exists and 0. Let's say f prime of 0, f double prime of 0, f third derivative at 0, f fourth derivative at 0, and so on. They all exist. And are 0. So the function is differentiable of every order and all derivatives are 0 for this specific function. So what will be the Taylor series then? So now that I know all derivatives exist, I will be able to construct the Taylor series here. The Taylor series on the right-hand side, I am able to construct it. What will it be? That's the Taylor series at a equals 0 will be f of 0 plus f prime of, okay, let me say here 0 for x less than or equal to 0. So f of 0 plus f prime of 0 plus f double prime of 0 over 2 factorial x squared and so on. Now f of 0 according to the definition of f of x is 0 for x less than or equal to 0. So f of 0 is 0. F prime of 0, f double prime of 0, all these terms, we said that you can show as an exercise that they're all 0. So then I will have 0 plus 0 plus 0 times x squared plus 0 times x cubed, which is 0. So t of x equals 0 for every x. So that means f of x and t of x. Now the question was whether f of x and t of x, the function on the right-hand side, if I call it t of x, the question is f of x and t of x, are they equal for x close to a? And a is 0 in this case for x close to 0. Can I say f of x and t of x are equal? Where t of x is 0, identical is 0, but f of x is not identical is 0. So no matter how close x is to 0, if x is positive, f of x will be e to power minus 1 over x, and that will be non-zero because exponentials are always non-zero. So regardless of how close you choose x to be 0, f of x and t of x will not be equal because t of x is 0, but f of x, if x is positive, will be an exponential function, which is non-zero. Exponentials are always positive. No matter what the power is, exponentials are always positive, and therefore they will not be 0. So we can say f of x will not be equal to t of x for x bigger than 0, since e to power minus 1 over x cannot be 0. Exponentials are always positive. And that means 2 star does not hold That means f of x is not analytic at a equals 0, although it is differentiable of every order at this point. Because no matter how you close x you choose to be 0, x is always allowed to be on both sides of a. So that's why we call it open interval containing a, because in order to because we want to make sure that x is allowed to be in both sides of a, left side and right side. No matter how you choose how small you choose your neighborhood, x is allowed to be on both sides of a, left side and right side. A is 0 here, so x is always allowed to be positive. But here, if x is positive, f of x will be e to power minus 1 over x. F of x is e to power minus 1 over x for x positive, and that is non-zero, but t of x is 0. So f of x and t of x are not equal to each other in this case. And therefore, the function is not analytic at a equals 0. So the answer is, the summary is, if the function is differentiable of every order, it is still possible that it is not analytic, but it will happen in very rare cases, very rare cases. Normally, in the standard functions that you're familiar with them, you learned about them in calculus, pre-calculus, exponential functions, trigonometric functions, polynomials, etc. For those functions, the function is analytic. The functions that I just mentioned, they are differentiable of every order on their domain, and they're also analytic. But in rare cases, it is possible that the function is differentiable of every order and not analytic. And this function that we provided here, I think, is the most famous example of such a function. Okay, guys, so today we learned about some basics about power series, Taylor series, analytic functions, and Taylor series of some particular functions that we'll use next time, like e to the x, sine x, cos x, 1 over 1 minus x. So what are the Taylor series of these functions? And what are the radius of convergence? We also learned about radius of convergence. So these concepts you learn in Math 114, but I thought maybe it's good to have a review so that we'll be ready to apply this concept of Taylor series and power series in order to solve ODEs. So if you want to use this concept to solve ODEs, first you need to know about these concepts and the basics of these concepts, such as radius of convergence, Taylor series, analytic functions. So that's why I wanted to give you a review this time, and next time we will see how to use these concepts to solve ODEs. Okay, guys, that's all for today. Thank you, and see you next time.